Hi, this is Dan from the Not So Secret Laboratory, and we'll be talking more today about Renaissance E2 Studio. Last time we learned how to download it, compile it, and some of the tricks associated with just navigating the menus and debugging, compiling, and so on. Today we're going to talk a little bit more about the code generator and some of the challenges you might have just getting to specifics as you go. I'll share my screen, and we'll get started. This is the familiar Renaissance E2 Studio window where over here in the Project Explorer, we've got a project open. This was a practice one we had earlier. This project has a lot of different generated files. If you see R_CG, that means Renaissance Code Generator. So these files were all generated when we clicked Generate Code in the Code Generator button. So let's go into the Code Generator and see how we ended up getting all of these files. That was done here. In the bottom, there's this Code Generator. And again, if you don't have this Code Generator button, then you need to add it by clicking this new Code Generator button, very visibly obvious. Okay, so Code Generator here, and we're going to double click on port, and that should give us a new menu, which we can scroll up here in this peripheral functions. We can see under port 0, 1, 2, whatever, we can say whether we want to use these pins or not. And in the data sheet, it'll tell you what these pins can do. Some of them can be used as a serial array unit, which can be configured as simple I2C, simple SPI, or as UART with another serial array unit together. And one of them is like a dedicated multi-master I2C pin, and that one can do things like clock stretching, which isn't referred to as clock stretching in the data sheet. It's called wait. Anyway, if you need clock stretch, then you want to be using, if you're talking to a device that does clock stretching on I2C, you need to be using that dedicated I2C-A port, like I2C-A0, I2C-A1. In this case, if we wanted to add these pins, we would just click them as and designate them as either an input or an output. If it's an input, you can enable the pull-up resistor, or you can designate this as an N channel. What is N channel? That's open drain. Typically, that's used for I2C. And you need to select that if you're going to be using I2C, which you would set up here under the serial menu. So if we click onto the serial menu, we could come in here and we have all these different serial channels based on the device that we've chosen, which in this case is an RL78G13, typical general purpose RL78 16-bit microcontroller. So here we can select channel 1 as UART 0. This one is UART 0. So it takes two, one for TX, one for RX. Makes sense, right? But in this case, the only one that's enabled is I2C11, which is a simple I2C master. And that's what this program is actually using. So when we're done, we click Generate Code, and then all this stuff just spews out. Well, what is all this stuff? So what we've got here is the port.c function, and that's going to just simply set a bunch of registers that allow you to mess with the register, set things as inputs or outputs. Like these pins here are being set up to be able to be toggled, and that pin toggling is used in debugging just to tell me that an algorithm is running or it's completed or something like that. So these were set up by that port code generator down here. It just spits out this code. You can see this CG port.h. This is the associated header file, and it defines these different variables, which might be useful to you. One of the important things to recognize here is this RCG serial function, and this is the designated serial bus here. So you'll find useful functions like RSAU0 create. What's SAU? Serial array unit. So that's going to actually turn on the peripheral inside the device. Some of these functions are a little bit low level, but usually these things can get called in the system init function at the very beginning. It creates the port, it turns the peripheral on, and that's something to be aware of. If you like add an ADC to your project, it's going to be powered on and like consuming power at the very beginning of your application. So you need to know how to read through these files and look for how to turn it off and turn it only on when you need it if you're in a low power application. So here we've got this function that can be called that will create this I2C11. It doesn't create anything. It's not an instance. This is not like a HAL with like object-oriented programming. This just goes and configures a bunch of registers on the device that allows you to do I2C communication. It doesn't create any structures. And then there's functions for sending or for receiving. in I2C's case, it's sending out pulses on the clock, right, on SCL, and it's just reading data back from the device. In the case of UART, it would just be waiting to get an interrupt that it's received. So each time you call one of these functions, the peripheral unit is going to try and do something. It's going to try and send some I2C data or try and receive some I2C data. And when it finishes that, it's going to set an interrupt inside the microcontroller. And this program is set up so that when that interrupt trips, an interrupt service routine is called. And so what interrupt service routine is called after master send? You have no idea. So what you have to do is go to this function called serial user.c. What is a user? That means that's the hint that you as the user actually have to do something with this file. This is essentially all the interrupt service routines. So this is an interrupt service routine here. It says that's called when this interrupt is serviced, right? So the best thing you can do is just try and find some example code that shows I2C. And they do have a lot of example code for Renaissance devices, but the more complete example code you can find, the better, and then it's less work on your time. A lot of these functions are a little bit lower level, so like if you need to have a delay between something, you'll have to implement that as like, you know, a while loop with no ops in the middle or something like that. A lot of times there aren't like, or you can be a little more sophisticated and use the timer functions, which you can access from here as well. So so basically, yeah, the timer options are typically a little lower power, right? So because you can halt. Halt is the way that you stop operation with I2C, other than stop. But stop kind of like just erases all your peripheral settings, so you kind of have to turn them all back on when you resurrect from that. So so yeah, it's a mess. Stop is a mess. Halt is really easy. It just halts the CPU. And you'll like that one. So you get these different interrupt functions, and this is all just totally auto-generated. Very little of this that I change. And in fact, in these programs, a lot of times you'll see here in this RCG serial.c, if you want to actually add something as a user, they want you to put it in between these two comments right here. Because if you go back in the code generator and you change a setting and you regenerate the code, it's going to change all this stuff down here. So anything you added is going to get essentially erased. It's not a bad idea to do like a commit before you do a code generator update. And then you can do a compare with the previous version and see if anything you had written as a user got overwritten. You can go back and just go through your line compare and git and just pull that change over. It's clumsy, but you know, hey, they're giving you a lot of free code, so you gotta like that. So anyway, you get all these functions you can call, and you get all these interrupt service routines that are called when things come back. And this is where you could just know that, you know, set flags, for instance, and let you know that UART's done. So in this interrupt service routine is called when a certain interrupt, when it finishes transmission, an interrupt is set in the microcontroller. It calls this function, and this function just sets this flag to 0. And if there's something else in your function that's waiting for that to go to be set to 0, then the program will proceed from that point. So this is just some of the things to be aware of that you'll see here. This WDT stands for watchdog timer. You can set up a watchdog timer. And just a couple other interesting things here. We have some interrupts. We have the ADCs being used here, CGC, which is a little over my head, and a timer. So these are all useful things that you can generate just from the code generator. Now let's talk about some of the less obvious things. Let's talk about when you go to actually run this code. So let's just say in a typical example, you're just going to click the debug button, and the code's going to start. And if you've got your debugger plugged in and your microcontroller powered on, the debugger will come up and it'll stop at the first line in assembly, and then it'll stop also at the first line in main unless you disable that in the debugger settings, which you showed last time. Where those are, you have to search around for that stop at main or whatever. Anyway, I'll click start here. So the program's running. And let's say I'm running and I find a problem with the program. And what I'll do is I'll typically go back to the code and I'll start editing. And what did I forget to do? I forgot to turn off this debugger. So now I'm going to go back. I finished my code. I got it ready to compile again. I'll click this debug again. And it says a previous GDB debug session is still active. You idiot, you forgot to turn off the debugger. So it says, do you want to terminate all previous sessions? This is like a roll of the dice. Sometimes it works, but most of the time it doesn't. I'll say yes and see what it does. In this case, it's probably going to work because I'm recording a video. It's just basically going to shut off the previous debugger and start a new debug session. But 9 times out of 10 for me, if it's been a little while, if something's gotten unplugged and plugged back in, it will fail. And then it will fail forever after that. It'll say, oh, there's a session that's active, a session that's still active, and it's not clearly not running, right? Like you'll hit stop and there's nothing running. So what's going on is there's just still a service going on. So I typically I just do a Control-Alt-Delete, an open task manager. In the task manager section, then, oh, I have to start a debug so you can see it. Inside the task manager, once this starts up, there will be a service. Look on details here. It's running called e2 server gdb.exe. And if it's stopped here, but this e2 server gdb.exe is still existing here, that's your problem. So you just click here, end task, and that will stop that Renaissance debugger and you can start a new one. It's a great little trick to get around a bug in the program they claim does not exist. And that competent people would never run into it. People like me who forget to turn things off definitely struggle with that. Okay, so we covered that one. Let's talk about watch expressions. Oh yeah, this is a good one. We're going to start another debug session here. So one of the really useful things with E2 Studio is the ability to have this real-time refresh. So while the program is running, the program will periodically pull the microcontroller and get the value of a certain variable. And you can just see that variable updating live without having to stop it and look at it, stop it and look at it, and start it again. It's a really useful feature. So we go into expressions and we find something in main. I don't know. Let's go back. Oh, this is pretty much main right here, oximeter.c. Oh, what's a variable in here that we've got defined at the top? We've got some variable called previous breathing rate. Previous BR is just always 0. Let's do sample log. All right, so we'll try looking at sample log. So let's go back to the debug view here, and we'll go to watch expressions. I've got my finger on this device because it's a pulse oximeter. So I'm typing with one hand here, sample log. Okay, so sample log was 10 the last time we paused, right? So if we click pause now, it'll update, and it says 20. So let's say we want that to update live and just kind of see what's happening to it over time. We can real-time refresh that. So we should just say real-time refresh. I think I would just add it to a chart. How do we get that to work? I'm not sure. Anyway, you get the real-time refresh to work. Add watch expression. It's not that one. There's a way to get real-time refreshes to work. But one of the problems with them is that, oh, enable real-time refresh. There it is. Okay, so this is, you can clearly see now, this is just updating. It's just polling periodically. This is actually updating quite frequently, about 4 times a second. So you're just getting the idea that it's changing. If you wanted to see it, you could add it to a chart, right? So we can do add it to a chart, and we get this chart appearing down here, and we can just see what this variable is doing in time. It's just jumping around between 10, 20, 30, and 40, sort of randomly. Because it's happening really fast inside the program, you can change the refresh interval to try and track it a little bit faster. So let's just change that real-time refresh interval to 100 milliseconds and see what happens now. Is it just stepping up and coming down and stepping up and coming down, going from 0, 10, 20, 30, 0, 10, 20, 30. That's what it's doing. Okay, so now, if you want to just disable real-time refresh, it's great. Occasionally you'll have some bugs here where you'll basically have to like stop the whole debugger and restart it because this isn't working. You might have 2 things refreshing or whatever, and maybe they fix these bugs, but occasionally you might have some problems with if you enable the real-time refresh and then you do something, it might cause an issue. So if it causes an issue, sometimes you'll have to stop debugging and restart if there's a problem with the real-time refresh. Okay, so that's that. Now you know about real-time refresh and the chart, which we mentioned last time but didn't actually show. You'll love the chart, especially if you got something going up or whatever. So, and also useful feature, if a variable changes, it turns yellow. So if you have a whole bunch of variables here, if it gets a new value and it's the same, it'll clear, so it won't be yellow anymore. But each time that variable changes, it'll be yellow, and the same goes for the IO registers. If an IO register gets updated, it'll turn yellow. And the next time you pause it, if it's the same, it won't be yellow anymore. Those are really useful things. What else do we got? Oh yes, optimization bugs. So let's talk about that. The different E2 Studio. You can open up multiple E2 Studio windows, and you can have a different workspace in each window. And that's really useful because you're not allowed to have projects with the same title. So you can't open up the same project in twice in the same one. So like if I had like downloaded one version from Git and opened it up here and then downloaded another version like on a different branch and wanted to see both of them here, I couldn't do that if they had the same titles. So I could just open up a separate window with a separate workspace over here, and we just flip between the two windows, and that'll be sufficient for me to switch between like two different versions of the code. So that's actually useful. So we're going to flip over here to this project. This is a very complex project. It's a device I'm working on at Renaissance, and you can reconfigure on the fly every single serial bus. It works like a GPIO expander, level shifter, everything. And we basically use the code generator repeatedly to generate snippets of code that we then brought in here. And so you can see we've just labeled them. The first time we generated it, we just relabeled it to this, and then we changed the configuration, generated it again. And now we have all the code that we need to disable SPI and turn on UART, for instance. So now it can respond to commands and change those on the fly. So that's kind of cool. The reason I showed you this is that there's optimization going on here. So in this device, contrary to what I showed you in the previous video, optimization is not here. That's the assembler optimization. What optimization you care about is up here in the compiler settings. And this device is set to speed precedence. And the reason for that is that I'm using SPI slave. So I'm setting up the RL78 to actually respond to another I2C master. And that works only at relatively high speeds. And it turned out I really couldn't get it to work at all without going into speed precedence for the debugging mode. So I set that up here. When you enable speed precedence, occasionally there are small sections of code that just get skipped over, like the compiler thinks, yeah, that's not doing anything, and it'll just not run it. So if you find that happening, the typical fix will be to do something like, let's say there's a short if statement or something like that. Then what you would do is just drop a no-op in there. And that no-op forces the compiler to include this whole if statement. It just can't, because it can't skip it, because these are used as timing, like delays and things like that in programming. So if you ever have a problem with the optimizer, just slap no-ops everywhere. It's just one of those things that the applications engineer would tell you that never shows up. Okay, so that's done. Generated code, we talked about that. I2C code, what works, what doesn't. Okay, I2C is a little touchy, and you have to configure the timing yourself in a lot of these things. And so that's something to be aware of, and definitely reach out. If you have any problems with I2C, just reach out to the applications engineers and have them talk to them. As I mentioned before, the serial array units don't do clock stretch. They don't support it, but the dedicated I2C multi-master channel does. So that's the most important thing to know there. It works at 100 kilohertz, 400 kilohertz, and some of the devices even work up to the very high speed modes, like the megahertz levels. SPI, Renaissance has like a knockoff version of SPI called CSI. I don't know if there was some licensing issue or something like that, but it just means SPI. It works the same way. The only difference is SPI modes, like they're labeled on Wikipedia, are like SPI 0, 0, no, SPI 0, SPI 1, SPI 2, SPI 3. And it has to do with the polarity of the clock and whether the data is latched on the rising or falling edge. And that is not the same as the CSI modes, which are 1, 2, 3, and 4, and completely different. So you just have to look those up and check them. So CSI mode does not equal SPI mode, but essentially it's just SPI. It works the same way. Read write works the same. One thing to be aware of with the serial array units is that you have to clear, it's like a shift register, and you have to clear that. If you don't, it's a problem. So hopefully your generated code has that and it clears that. It's just something to be aware of if you ever have a problem with that. All those serial channels just use the same shift register to read in data. So if you're stopping or restarting, whatever, just got to clear that thing out. One thing to be aware of also with this type of microcontroller is there's a lot of registers that like report a value, and like an interrupt, and you're supposed to clear that interrupt. So you could just think, oh, I could just write 0 to that interrupt register and it would clear the interrupts, but it doesn't. There's always like a separate register that you write to clear the other register. So as you read through the data sheet, when you find a register that like reports something, in the back of your mind, think, okay, I gotta keep looking for the register that clears this one. And then you'll manipulate that one. And a lot of times it's being done. You can look at the code generator and try and figure out, you're like, this register is getting cleared somewhere, but I can't see any writes to this register. Where is it getting cleared? There will be this other stealth register that's doing that clearing of the data. So that's something just to be really aware of as you're programming. Okay, which is the register that actually clears this one? And there are good reasons for setting the architecture up like that, so it's very stable, so that you can't be writing to something that something else is trying to write to. Write to this one, it queues the operation, so when nothing's happening, then it will clear it. So it's a good design, just something you have to be aware of if you're a doofus like me and you don't know anything about programming. All right. Error handling. Some of the I2C doesn't particularly have good error handling, so you might see like an error handling ISR. So let's see if we can find one, like channel 00 ISR. This would be called user something. This would be like channel 00 user.c, but I relabeled it ISR. So this one, like here, you just control click to get there. It just sets a flag that lets you know there was an error. It's not actually doing anything. It's not going in and clearing the error that was set in clearing the register that clears it's not writing to the register that clears the error register. It's just setting a flag in software that says, hey, there was an error. That's kind of on you. You got to know, hey, I got to go back and clear that error. So a little bit of data sheet reading goes a long way for that. I think you'll find that I've actually added some of that here. You can see these here where I'm reading back the error and I'm clearing it. This is just some error handling here. There might be some in the generated code. You might have to add some of your own. Just a good thing to be aware of. For instance, if you're writing to I2C to like a sensor or something like that, and you get a NAC error, you got to handle that. So if you don't handle that NAC error, then your code's basically going to be hung until you handle that. So just good to be aware of. What else? Oh, UART. Okay, so everybody loves print debug. Like if I come from Arduino, then I just have to print everything. I don't have line debugging, but there are some times where you just have to print. Like if you want to look at a giant array, or you're interacting with a script that's sending things to your, like I have a version of this code over here where I just send canned data to the device, and it runs the algorithm on the device, and then it spits back the results of the algorithm, like computing heart rate or something like that. And then there's a Python script on my PC that's sending the data out and storing the algorithm outputs back. It's a great way to verify, but you can't do that with debug, right? So you have to do it with UART. So just the tricks with UART here. This is the way I'm doing it. I've got this. Oh, can I zoom that at all? No, it's not going to zoom. Okay. Basically, we're just going to set this buffer to 0. And then we're going to fill up this buffer with a bunch of values that we want to write. And then we'll figure out what the length of that buffer is. And we'll set some flag to busy. And then we'll set it to send. And 100 to 1, when this thing's done sending, it calls an ISR. And in that ISR, it sets the UART flag, not busy. So that's basically how I'm doing print, right? In Arduino, it's gives you a lot of control here. You want to do this with ASCII? I don't know. I'm just writing like I'm just writing binaries here, I think. No, I think I'm writing text. I think I'm writing text. Yeah, this is ASCII text here, so that's good. But you can do it either way. So yeah, that's basically how you're doing print debugs. Try to get some example code if you can. Interrupts on off. You'll see in some places where you want to disable or enable interrupts. And so there's these like You'll see this EI colon means enable interrupts, or DI is like disable interrupts. Those are just like little macros that call enable or disable interrupts. You'll see that stashed in your code in different places like that. Like if I just click DI here, just right click. This is really useful if you're not familiar with this. Search text in the project. You'll find everywhere in the project that you've got disable interrupts, right? It's down here in source, somewhere in this project. Oh, it's finding everything. You know, what about this? What if we just grab this little piece right here and we search text the entire project? And there we go. We found this one, and there in system init, it's actually disabling interrupts and then doing the system init function. So you can see that. That's kind of useful. So here's where we added our little extra thing. Alternatively, you know, if you're not really familiar with Eclipse, I can click on this variable right here, and I can look at references or declarations. This is where the variable is declared. I can see exactly where this variable is declared here as an extern in the header file or here in C, or I can just look anywhere it's used. That would be references, and I can see anywhere it's used. It's used in all these places. So that's actually a really useful feature about Eclipse. And of course, you've got your autocomplete, which I think is control space or something like that. Yeah. Anyway, you got your autocomplete, which is great. What else do we have to cover? Well, we're about halfway through, so we're going to call it quits on this video. Come back for the next video, and we're going to cover a few more things related to like changing the device and increasing the stack size and seeing the code size and a few other things like that.